Welcome to ChemExam Explained, where the aim is chemistry clarity, exam mastery. In this video, we will be looking at CSEC Chemistry, May-June 2024, question 1. Now, before we even start the question, let me say this. When you get these questions, you must go through because we have important information in the question that we will need to answer the questions. So let's start by looking at this section here. It says that sodium thiosulfate solution, which is Na2S2O3, reacts with dilute hydrochloric acid to produce sodium chloride solution, sulfur dioxide gas, solid sulfur, and water. So pay attention to this section here. Now to look at the experiment. So to investigate the effect of temperature on the rate of reaction, Paul performed different experiments using sodium thiosulfate and dilute hydrochloric acid. For each experiment, the same volume and concentration of sodium thiosulfate and hydrochloric acid were reacted, but at different temperatures. So we're using temperature to study the rate of a reaction. That is why the concentrations were kept constant. Now the temperature was measured at the start of each experiment, and the thermometer reading for the experiments 3 to 7 are shown in figure 1. So here we have figure 1, which represent our temperature readings. We'll come back to look at the values. 1 part A. Define the term rate of reaction. Rate of reaction can be defined as the change in concentration of product or reactant over time taken. Or you could use the formula, rate of reaction is equal to change in concentration, again it could be change in concentration of product or reactant, over change in time. Now the unit for rate is moles per dm cube per second. Let's see why. The unit for concentration is moles per dm cube. And the unit for time is seconds. So the unit for rate is moles per dm cube per second. Let's continue. 1 part B, and we look at part 1 and 2. Now they're asking us to write a balanced chemical equation for the reaction between the sodium thiosulfate and the dilute hydrochloric acid. Now please remember that this information was given in the question at the start, so we can write our reaction now. Now they want a balanced chemical equation. What does that mean? Well, 1, you want the correct stoichiometric ratios. Those are the numbers that goes in front of the molecules or compounds. And 2, you must have the correct state symbols. So to write this chemical equation, we're going to write sodium thiosulfate Na2S2O3 plus hydrochloric acid aqueous to give you sodium chloride aqueous plus sulfur dioxide gas plus sulfur solid and water in the liquid state. So these are our state symbols. Now to ensure it is balanced, you have 2 sodium here. We had 1 here, so we have to put 2 in front to make sure the right hand side is balanced with the left hand side. We now have 2 Cl. Over here we had 1, so we put 2 in front of HCl to ensure we now have 2 Cl on the left hand side, similar to what we have on the right hand side. We then move to sulfur. You'll see that we have 1 sulfur atom here in SO2 and another by itself in the solid state. So we have 2 sulfur atoms on the right hand side, and if you come over here, you'll see we have 2 on the left hand side. We then move to oxygen. We have 1, 2, and 3 atoms of oxygen on the right hand side, and we have 3 on the left hand side. We have 2 H's on the right hand side, and remember when we balance this one, we now have 2 H's on the left hand side. Now the reason we balance the equation is to ensure that the number of atoms on the left hand side is equal to the number of atoms on the right hand side, and that is due to the law of conservation of mass. Let's look at part 2. Describe a test and state the observation that can be used to confirm the presence of sulfur dioxide gas produced from the reaction. Alright, so we're seeing that we have sulfur dioxide gas. The first thing we must know about sulfur dioxide is that it is a reducing agent. So to test for a reducing agent, we need an oxidizing agent, and we could use acidified potassium dichromate or acidified potassium manganate 7. So the potassium dichromate is an oxidizing agent. Let's put oxidizing agent. And the way that we're going to test for the SO2 is to allow the gas to pass through the solution of the acidified potassium dichromate. Or you could simply say you bubble the SO2 gas through the potassium dichromate and observe. Now the observation should include the following. You must know that the dichromate ion is orange. Why? The reason it's orange is because the Cr in the dichromate is in the +6 oxidation state. When the dichromate reacts with the sulfur dioxide, it will be reduced from +6 to +3. And when we have Cr in the +3 state, it is green. So the observation that you should see is your orange solution changing to a green solution. Let's continue. 1b part 3. Determine the mass of sulfur dioxide produced when 50 cm³ of the gas was collected at STP. Let's start by looking at the information that was given. Now the first thing I see that is an issue is the relative atomic mass of each of the elements. For sulfur, we get 32. For oxygen, we get 16. Now, relative atomic mass has no unit. So I would have preferred if they had given us the molar mass, which gives us a unit of grams per mole. And this will be useful in our calculation. We also get the mole of gas at STP. So 1 mole of gas occupies 22,400 cm³ at STP. We're going to convert this to dm³ as well as the 50 cm³ here. So both will be converted. So the info that we have the volume of gas at STP to be 22,400 cm³. We'll convert a dm³ by simply dividing by 1,000. We get 22.4 dm³. The volume of SO2 is given to be 50 cm³. We divide by 1,000 to get 0.05 dm³. We are going to calculate the molar mass of SO2 from the molar masses given for sulfur and oxygen. So that is 32 for sulfur plus 2 times 16 to give us a molar mass of 64 grams per mole. We can now move ahead to find the mass of sulfur dioxide, but before we do, we need to calculate the moles of SO2 first. So we're going to use the formula. Mole of SO2 is equal to volume in dm³ over 22.4 dm³ per mole. So we have our volume to be 0.05 dm³ divided by 22.4 dm³ per mole. So if we work out our unit, we'll cancel dm³ with dm³. We're left with per mole, but of course, this will be brought up to be mole. In other words, 1 over mole is equal to per mole. So if we have per mole down here and we bring it up, it becomes mole. So that's why our unit becomes moles. So when we divide 0.5 by 22.4, we end up with 2.23 times 10 to the minus 3 moles. For step 2, we're going to find the mass using the formula moles equal mass over molar mass. We make mass the subject of the formula and multiply the calculated mole by the molar mass of SO2. And that will give us 2.23 times 10 to the minus 3 times 64 to give us the mass of 0.143 grams. Now you'll see that again, our units work out to be grams when mole cancel mole. That is why it's important to use molar mass, because we have units to use in your calculation to get the mass of sulfur dioxide. Let's continue. 1C part 1 and 2. So for part 1, we're given a table and we have our experiments, number of experiments, we have temperature, we have time, and we have 1 over time, which is per second. So these values we would have to work out using 1 over t. So we are to record the temperature readings for each of the experiment in figure 1. So we say when we have 13 here to 14, we see that that is 1 unit. And if we divide that by the number of marks here, we'll get 0.2. So we have 13.2, 13.4, 13.6, 13.8, and 14.0. So that is 40.0. You put that in the table. For experiment 4, we start at 20. So we have 20.2, 20.4. But notice that the reading stops in between these 2 points. So that is going to be 20.5. And that is placed in the table. For experiment 5, we have 26.2, 26.4, 26.6, 26.8, and 27. And that is 27.0. That is placed in the table. For experiment 6, we have 32.2, 32.4, 32.6, 32.8, 33.0, and that is placed in the table. On our last experiment, we can start our reading from 35. So we have 35, then 35.2, 35.4. Again, the reading is between these 2 points. So we have 35.5, and that is placed in the table. So we placed in the temperature reading for each of the experiments shown in the table. Part 2, calculate to 3 decimal places the rate of reaction for each experiment, given that the rate is 1 over time. Record your results in column 4 of table 1. So you can see that if we have seconds here, which is our time, we need per second. So 1 over time is equal to 1 over second, which is our unit is going to be in per second. So this represents our rate of reaction. So let's go. If we say 1 divided by 59, we get 0.017. 1 divided by 50, we get 0.020. Now ensure that you have 3 decimal places because you will lose marks. 1 divided by 40 is 0.025. 1 divided by 24 is 0.042. 1 divided by 15 is 0.067. 1 divided by 11 is 0.091. And finally, 1 divided by 10 is 0.100. Once you have these values in, you will get your full marks. Let's move on. 1D Part 1. Using the axes provided in Figure 2 on page 7, plot a graph of rate of reaction versus temperature for experiments 1 to 7. Draw a smooth curve through the points. So what we'll do is, we'll examine the table one more time, and these values will be placed on the x-axis, and these values will be placed on the y-axis. So we'll go back here, and the next thing to note, they require a smooth curve. So ensure you read the questions properly. They want a smooth curve, not a line of best fit. Let's see what's going on here. On the y-axis for our rate, we have 0.01 for every 2 centimeters. So we have 0.01 per second for every 2 centimeters. So if we divide this by 10, because we have 10 boxes in between 0 and 0.01, that will give us 0.001. So each of these small boxes is 0.01. On the x-axis, we have 5 units for every 2 centimeters, which again is 10 small boxes. And that will give us 1 over 2, which is 0.5. So we go 0.5, then 1, 1.5, then 2, 2.5, then 3, 3.5, and so on. And that is what we're going to use to plot our points with the temperature and the rates. Ensure that you plot your points using a dot and a circle or an X. Now, once you plot your points, you then draw a smooth curve between the points, and that should satisfy the question. 1D Part 2. Using the graph you plotted on page 7, explain how the change in temperature affects the rate of reaction between sodium thiosulfate and hydrochloric acid. Let's look at the graph. You can see that as temperature increases, the rate of reaction increases. You can see the graph going in that direction. So that is your answer. As temperature increased, the rate of reaction increased. All right, so you could say that the rate of reaction is directly proportional to temperature. This is the end of Chemistry, May-June 2024, question 1. Please remember to like, subscribe, and click the notification bell so that when new videos are uploaded, you will be notified. Thank you.